All right. So we are in the second part of this unit. And so we learned all about dot structures, learned all about shapes. But now we have to add some kind of complicated things, which are like you really just need to know a pattern for them. But the concept is a little bit different. So the concept here is hybridization. So a hybrid, so think about a hybrid car. A hybrid is a mix of two things. So a hybrid car is a gas and electric vehicle that is mixed. A hybridization is a mixing of the orbitals within an atom. So, like if you remember, we had the blocks, right? So S, P, D, F. So that's how we do electron configurations, S, P, D, and F. Well, those electrons are sort of supposed to be in certain areas. And so you have like electrons that are supposed to stay over here in the S, and then you got electrons that are supposed to stay over here in the P. But then what happens if I take this electron here and it hops over here? That is going to be hybridization. So that electron hops over here. And so now what happens is that you have more bonding sites. So, like a bonding site is a place where another electron can attach. So now we have a bonding site here, 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 and here. So we now have an extra bonding site because these spaces around the nucleus are working together. And so that's what hybridization is. It's these orbitals starting to blend together. Now, that's super complicated. You just need to really be able to figure out what the hybridization is. And I got a really easy way for you to do that. So let's look at the notes here. Hybridization occurs when an atom forms more bonds than would be expected from its number of valence electrons. The bonds form because some electrons are promoted to an excited state, which increases the number of bonding sites. So when I just drew those boxes and I moved an electron, I was promoting that electron. So when I moved that electron, it got promoted. Excited state just means the electron is not where it's supposed to be, right? So like it just moved around. Now, what's this stuff about more than expected? Well, if you look at something like carbon, it has 4 valence electrons. Well, you would expect that carbon could make an attachment in 4 places because that's what we've been kind of doing. But if we really dive in and we look at the way carbon is set up, carbon is it is not quite like that because carbon has 6 electrons. So that's going to be 1s2, 2s2, 2p4. So if I, sorry, not 2p4, 2p2. Ugh, horrible. If I draw that out, here's the 1s, and it has a couple of electrons. Here's the 2s, and then here's the 2p. Well, where's the 4 bonding sites? There aren't 4 bonding sites there. I've got a bonding site here, and I've got a bonding site here. That can't bond with anything because it needs an electron to bond. So we don't have those 4 bonding sites. We have one here and one here. So bonding site is an electron where another electron can attach. So that's what I was saying earlier. This electron then is going to move, and it's going to create, let's draw it in blue because this is the one that's affected. So right there. So this orbital here, one of its electrons hops over here, and now look, you just created another bonding site here, and you created another bonding site here. So we draw carbon all the time with 4 things attached. Well, for that to actually happen, it needs 4 spaces, which it now has. That's what's going on in hybridization. Okay, so this is what we see, and this is what actually happens to get those bonding sites. Okay, now it gets way easier for you, and so don't worry about that. That's just the background. How do you determine it? Okay, really, really easy. So look at my notes here. This is definitely on the test right here. This part is on the test, but this is something that if you can draw a dot structure, remember I talked over and over again that the dot structure is super important. You can do hybridization. So count the number of sides on the central atom that has shared or lone pairs present. If it's got 2 sides, 3 sides, 4 sides, however many sides it has doing stuff, that's its hybridization. So here's the way to do it. Look at my thing here. You want to remember this. You want to be able to write that out right there from memory on a test. So if you can do that, if you can write this out, then you can always figure out hybridization. Okay, so what you do is you count how many attachments are on your central atom. So if we look here at this example, we'll pick one of the borons. So here's your central atom. How many things are attached? So all we do is we count attachments, all right? So we're going to look at the attachments, and then that's going to determine how far over you go. So we have 1, 2, 3 attachments. The double bond is going to count as a single attachment. So I don't go 1, 2, I just go 1. So the double bond just counts as 1. Now I'm not doing these 2, I'm just going to do the first one because they're resonance structures. So that has 3 attachments. It has 3 attachments. So what I do is I come over here and I look at the thing I told you to memorize, and you just count over. 1, 2, 3. And then you take the highest value for each letter. So this would be sp2, which means that the s and the p orbitals are blending. So if you look at this, you can see it sort of maxes out at D2 because that's the most blending that can happen. So this needs to be memorized because you're going to end up using this on to figure these out. If you know that, not that hard. All right, so determine the hybridization of carbon tetrachloride. Now, I guess I should show you this diagram real quick. I did put it in the notes. What the heck? That's what's actually going on. See how those colors are overlapping? So here's the overlap is happening. This overlap is the hybridization. So they're not by themselves, they're overlapping. Once again, more than you need to know. You need to be able to do 6. That's what's going to be on the test. Not a Y, but a like, hey, what's the hybridization? So carbon tetrachloride. Let's do that. Carbon tetrachloride is CCl4. So let's dot them up. Okay, target number. What's the target number on carbon? It's 4. What's the target number on chlorine? I say valence number on carbon is 4. Valence number on chlorine is 7. So there's 4 of them. So that's 28 for the chlorines. 32. There's our target number. What do I got here? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So I have 32, so it's done. All right, so we're talking hybridization here, right? So it said hybridization. So what do? Count the attachments to the central atom only. I have 1, 2, 3, 4 attachments to the central atom. I don't care if they're single, double, or triple bonds. They all count as 1. I come over here. 1, 2, 3, 4. I take the highest value from each letter. This is going to become an sp3 hybrid. It's blending the s orbital with the p orbital, and it's going to go up. It's going to push into the p3. You don't need to know all that. You just need to know that it's called an sp3 hybrid. Okay, so once again, going back to my little device that you need to know for the test, should have probably wrote that this is probably not the most important thing on the test. It's actually this. So, okay. Describe the hybridization for xenon tetrafluoride. I want you guys to try that one. So pause the video, try it, see if you get it right. Well, let's give it a go. Xenon tetrafluoride is XeF4. Okay, so we're going to have to draw the dot structure. So not a ton of space here. So let's go like Xe, and then let's do these fluorines. And let's dot them up like so. So that top fluorine is going to be hard to get those electrons on there, so I'm going to have to give me a little more space here. Like that, like that. Okay, there we go. So let's do a target number. So target number, so your xenon is 8. It's actually noble gas. That's kind of rare for seeing noble gas bonding. And then you got 7 for fluorine. So 4 of those. So we're actually looking at 36. Well, let's see what we got here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So I'm shy by 4 electrons. So I'm going to have to put 2 lone pairs on Xe. So I'll put one there, and then I'll put one there. So this is going to create an AX4E2. So I'm going to count the attachments, and then that's going to show me where to go. You could just look here, right? Like add the X's and the E's, and there you go, 6. Or you can count the attachments. It doesn't really matter. 1, 2, 3, 4, 5, and there's a bond there, 6. There's 6 things attached. So might be easier just to look at your AXs, since you know how to do that, and then that might get you the answer a little easier. So this is telling me, hey, there are 6 attachments. I need to move on that chart over 6 spots. Okay, so we don't have the chart on this page, so let's go ahead and write it down. Where am I going to write it down? I'm going to put it down here. So from memory, my chart is S. Then you get P1, P2, P3, and then you get D, and then you get D2. So we're going to count over 6 spots. 1, 2, 3, 4, 5, 6. So you take the highest letter from each one. So it's S. You always get the S. P3, D2. And that's as big as they can get. So this is going to be an S, P3, D2. So this one has all kinds of overlaps and blending happening because it's a very, very complicated structure. And I need 6 bonding sites, and that's really hard to get 6 bonding sites. So that's what's going on here. You need to be able to do this piece, and that really means that you need to know how this right here, right? So that's like super important. All right, I'm going to pause it here. We'll pick up with sigma and pi bonds, which are super easy on the next one.